Students, today I am going to discuss the position of voids in solid chapter. As we learned in the previous video, the arrangement of atom in 3D in FCC or CCP, we see the arrangement like A, B, C, A, B, C. A layer is the 2D arrangement as we have discussed in the previous video. After first layer, the second layer B is formed by covering tetrahedral voids, tetrahedral voids, and the C layer is formed by covering octahedral voids. So students, octahedral voids as we know is by 6 atoms, formed by the 6 atoms, and the tetrahedral voids is formed by the 4 atoms made up of 4 atoms. So we already discussed all the things in the previous video. Let's we see the position of voids in CCP or FCC cubic shell. So at first we discuss about the tetrahedral voids. Tetrahedral voids. Tetrahedral voids is always formed at the body diagonal. Body diagonal, and the total number of tetrahedral voids at the body diagonal is 2. So total number of body diagonal is 4. So number of tetrahedral voids becomes 8. So let's see how the tetrahedral voids are formed. At first we draw the cube. So for tetrahedral voids, as we study, it is found at the body diagonal. So here is the first atom, and one on this face, one on this face, and one in the back face. If we joint 3 in this form, so it becomes triangular, and this atoms present at the corner if joined like this, so it will form tetrahedral voids. And voids form, here is the voids form, and it is formed at the edge length. So it is formed at the edge length. Same tetrahedral voids formed at this particular corner if we consider this particular body diagonal. So we'll again one tetrahedral voids formed at this particular corner. See here. So let's we consider one atom from this face, one from this face, and one from front face. So this again becomes by joining this and one atom at present here. So all join, so it will forms a tetrahedral void. So students, if we consider this is the body diagonal, so tetrahedral voids is always formed at the body diagonal, and there are 2 tetrahedral voids formed at each body diagonal. So write down the points. There are 2 tetrahedral voids at each body diagonal, and number of body diagonal is total 4. 1, 2, 3 and 4. One from this side, one from this side, one from this side, one from this side. So suppose you are sitting in a room and there are 4 corners. So from this corner to this corner one body diagonal, and all 4 corners means there are 4 body diagonal present. So number of body diagonals is 4. So number of, and 2 tetrahedral voids form at each body diagonal. So number of tetrahedral voids form is 2 into 4 means 8 tetrahedral voids present in a, suppose we have a FCC cubic cell. So there are 8 tetrahedral voids are present in FCC or CCP structure. So in this way you can easily find out. Suppose we consider here it is the body diagonal and total how many R's present? Total 4 are present. We already read about this. So students, so tetrahedral voids from here to here root 3a by 4, and from here to here root 3a by 4. This is A. So in this way you can easily find out the tetrahedral voids in CCP or FCC cubic structure. Let's discuss the octahedral voids. Location of octahedral voids in cubic cell, in unit cell. One thing is so about the octahedral voids. At first, at the body center, one octahedral voids present at the body center, and at each edge center, at each edge point or center. So let's draw the octahedral voids, how it is the form. So let's see. Suppose we have one atom here and one atom here, this face and this face, one from this face, one from this unit cell. Suppose here is one unit cell, this face to this face, one from one in this face, one in this face. So at first we prepare by showing this form a base and this connected like this, and this again so there is a formation of, and here is the octahedral voids present. Octahedral voids form. Simply in this all face you can draw at body center. This is formed at the edge. One, I'm again trying to explain, like this. Suppose this is cubic unit cell. Suppose this is the edge, so contribution, suppose this is one direction, and 2, 3, 4, 1, 5 and 1, 6. So at each edge point there is the formation of one octahedral void. So total number of edges are 12 and the contribution of atom is only 1 by 4th. Contribution of atom is only 1 by 4th here. So student, at edge only 1 by 4 part is present under unit cell. Only 1 by 4 part is present in unit cell. So total number of edge is 4. Total number of edge is 12 and the contribution is 1 by 4. So total number of edge is 12 and contribution of atom is 1 by 4. So it comes 3. Now at the body, 1 present at the body. So see here, suppose by 1 present at this particular backside face, because it is FCC, 1 atom here, 1 atom back and 1 from front face. This is front face. So at first you can draw like this, and 1, 2, 3 and 4. 1, 2, 3 and 4. So at the here is the also octahedral voids present in the body center. So number of octahedral voids at each edge. So number of voids is, total number of edge is 12 and the contribution is only 1 by 4. So here is the, at the edge total number of voids is 3 and 1 present in the body, and at the body only 1. So total number of 4 voids form. Total number of voids is 4. So let's we discuss about the suppose we have rank, suppose we have rank is n, the number of unit cell is n. So if we find out the total number of tetrahedral voids, it comes 2n, and octahedral voids equal to n. So Z is the rank of unit cell. So in this way you can easily find out the number of tetrahedral voids and octahedral voids in the FCC or CCP structure. Total number of tetrahedral voids, if n is the suppose n is the 2, N is the 4. In this way you can find out the total number of octahedral voids or tetrahedral voids present in the any unit cell like FCC or FCC. Let's we discuss another topic. This is called the radius ratio, students. At first we discuss the radius ratio. At first, few important points regarding radius ratio is it is only for ionic compound like NaCl, KCl, zinc sulfide, etc. Number 2, radius ratio represent like this: radius of cation by radius of anion. So we do the main focus on it. Number 3, if radius of cation is higher, that means radius ratio will be higher. Next, as we know, radius of anion is greater than radius of cation. Next, if radius ratio for ionic compound is high, the stability of ionic compound will be high. So these are the few points. One more points is also, note down it. Number 6, if the radius ratio is high, or high means if the, in case of cation, suppose we talk about the radius ratio of cation is high, then coordination number also high. In case of radius of cation, C stands for cation. Suppose we have smaller size of cation, so only 1, 2 or 3 anions surrounded, because cation is smaller size and it is fixed in the voids. So bigger the size of cation, more the coordination number, means more number of anion surroundings, and greater the number of anion, more will be the stability of cation. Suppose, or the size of anion is more bigger than the size of cation, like this, because we know that size of anion is bigger than the size of cation. So it, suppose the size of cation is this, so anion becomes like this, or so many, means coordination number increases. Our next point is 3 points, or few points, mainly 3 are important for the stability of ionic compound. What are the 3 points? Ionic compounds. Note down only 3 points. What are the 3 points? Number 1, first point, cation and anion assume to be spherical in shape and must be touching each other. Next point is anion generally will not touch to other anion. Why? Because suppose here is the cation and we see like this, the arrangement of anion like this. So this is the negative, this is the negative, though repulsion takes place and energy becomes high and stability becomes low. So during the arrangement, the anion will not touch to each other for the stability of ionic compound. And the next point, cation must surround by maximum number of anion and vice versa. Because at the more and more number of anions surrounded to the cation, their energy decreases and stability increases. So let's see. As we know, the size of anion is bigger than the size of cation. So the packing done by the anion and voids occupied by the cation. So mainly the work of anion is packing because their size is bigger due to bigger size, like BCC packing, like HCP packing, like BCC packing, so on. And cation always occupies voids due to smaller size. Suppose we have this type of box, so we arrange at first bigger anion like this, and this small voids is occupied by the smaller cation. Next we discuss so student, we always fix the size of anion and only the size of cation vary. So size of anion always keeping fixed and the size of cation vary. In case of size of cation, it will be too small, so radius ratio decreases, stability decreases, coordination number decreases. Let's talk about, suppose we have a smaller cation like this. And suppose three anions like this, and here is the cation present in this voids. So at first we see which type of voids is formed. It is the triangular. If we put one ball over it, it becomes tetrahedral. So we know that if we consider the radius from this to this, so this is the triangular voids. So at first see here, from here to here. It is r plus r. This r for this particular radius and this r for this particular radius. And we know that, so the angle is 60 degree and this particular angle becomes 30 degree. Let's draw here also. Suppose this is the 30 degree angle and one perpendicular gives here becomes 90 degree. So this is the base and this is the base and this is the radius r plus r and this is the perpendicular. So according to formula, the math students very well know, base by hypotenuse is equal to cos 30 degree and base is r and r plus r equal to cos 30 degree. Cos 30 degree. Let's now we know that r equal to root 3 by 2 and r plus r and r minus this come here 3 by 2r equal to r and r 1 minus root 3 by 2 equal to r and r by r equal to 1 minus root 3 by 2 and it becomes 0.155. So in this way you can easily find out the radius ratio of tetrahedral, octahedral, BCC, so on. Let's summarize by making a chart of different radius ratio, voids of different radius ratio. So it is easy to remember radius ratio. Anion to cation. Anion to cation, and here is the radius ratio range. At first we talk about, suppose we talk about the linear shape, like suppose this is the cation and one anion is here and one anion is here. Suppose this type of shape is found, so this radius ratio 0 to radius ratio 0.155. Number 2, triangular voids, the radius ratio 0.155 to radius ratio 0.225. In case of tetrahedral void which is made up of 4 atoms, the radius ratio 0.225 to radius ratio 0.414. In case of octahedral which is made up of 6 atoms, the radius ratio comes 0.414 to radius ratio 0.732. And last, in case of body cubic center which is made up of 8 atoms, so their radius ratio is 0.732 to radius ratio is 1. So this is the summarized form to remember and find out the radius ratio of different voids. So students, in the next class we will discuss the defects of solid, and that is enough for today. Do all the question answer related to this topic of NCERT. Okay, thank you.